Thank you, Mr. Chairman. So I will present a work on a plate model, and we'll try to give some justification about it. So the motivation of this work is that I'm in a civil engineering lab, and we are considering very anisotropic plates. Typically, you have these carbon fibers reinforced plates. Here it's just cellular sandwich panels, and here it's a laminated plate made of thick layers of wood with orthogonal directions. This is called cross-laminated timber. So the motivation of this work is that in most of these plates, the transverse shear effects are important, and they will fail with transverse shear modes, okay, in bending. So if you're an engineer, this question deals with thick or, please, sorry. This question, you will deal with thick or thin plates as an engineer. If I'm a more theoretical person, the question is about, is it a first order plate model or a higher order plate model? So the thin plate model is a Kirchhoff-Love plate model, and the common assumption is that to say that the rotation is equal to the slope of the midplane of the plate. And this model is very ancient, and it's very well known, and it was also derived from asymptotic expansions. Okay, so it's the leading order plate model. The matter is that with this model, you don't have the transverse shear deflection, and you neglect the transverse shear effects in the approximation. Okay? And now, since you need to go higher order for having transverse shear effects, the Pandora's box opens. Okay? And this is why plates are generalized continua. And most structures are generalized continua, because there is the relation between the shear forces and the bending moment. Since the shear forces are the derivative of the bending moment, you have an internal length scale, and so it's a generalized continua. Okay? And so the engineering model for thick plates is a Reissner mean-lean plate model. And most engineers say, okay, this is just relaxing the rotation, the link between the rotation and the gradient of the deflection. And some other people say it's a Kossora medium, or Kossora plane. So there are various ways of seeing this fact. And just since there are numerous ways of deriving a Reissner plate median model, somehow you see that there is something which is, this model is kind of controversial. There are many papers dealing with trying to derive constitutive equation for this model. It turns out that engineers prefer this model because it has very natural boundary conditions. Okay? So my purpose here is try to derive the Reissner mean-lean plate model from an asymptotic approach, so perturbative theory. And I will try to convince you that if the plate is homogeneous, actually Reissner had a very acute idea of the transverse shear effects in plates. And when the plate is heterogeneous or laminated, you need a more general plate model, which is called the bending gradient plate model. So my talk will be organized as follows. First, I will perform formally the asymptotic expansion for a laminated plate loaded out of plane. Okay? A very simple situation. Then I will show that the classical approach for deriving like a strain gradient model approaches are not efficient in this situation, as well as the asymptotic expansion itself is not practical. Then I will build the bending gradient plate model with very simple considerations, and then I will try to build error estimates. I'm not a mathematician, but I will try to provide arguments to show that it converges somehow. Okay? And I will give a very short illustration with the cylindrical bending of laminates. So for the asymptotic expansion, I first said the 3D problem. I want to simplify my life. So I have a laminated plate, and the constitutive equation is monoclinic with respect to any horizontal plane, and this distribution is even. Okay? This means that the plate is mirror symmetric for engineers. It's a symmetrically laminated plate, if you want. And the transverse load is symmetrically distributed or anti-symmetrically distributed around the plate. So now the problem is actually skew symmetric with respect to the midplane. So it's a pure bending problem. I uncouples all membrane problem with respect to bending problems. So now this is the 3D problem. I want to reduce the dimension, so I will perform an asymptotic expansion. And actually, it's not a multi-scale expansion because the variables are strictly separated. So I will first perform a scaling. So the in-plane variable is scaled with respect to the span. And the out-of-plane variable is rescaled with respect to the thickness. So the small parameters is eta, the inverse of the slenderness ratio. You need to scale the out-of-plane loading, but this is just a matter of choice. And the main consequence of this choice is that you split the differential operator into two parts, the in-plane part and the out-of-plane part with different scalings. This is for the scaling. Now I will perform the expansion, which is considered as formal, and I will do only formal things there. So it is classical to assume that the displacement field is follow an expansion in the small parameter, like a kind of Taylor expansion, as well as the strain and stress fields. If you do that, you insert all those stuff inside the 3D problem, and you just identify order by order the equations. You get, for each order, auxiliary problems and macroscopic problems, plate problems. It's a cascade or succession of those problems. So I will this is formal. I will just show you how things are going, and this just gives you the overall picture of the result. So if you go at the first, most leading order, what you get as solution for the displacement is just a vertical displacement. This vertical displacement is actually the average of the full displacement of the plate through the thickness. So those brackets is just the integration through the thickness. Okay? And this displacement is only a function of the in-plane variables. So it's a rigid deflection, and there is no stress related to this displacement field. Okay? If I go on one order higher, what I get is a rigid rotation. So this rigid rotation is just, here you have the gradient of the deflection, so the rotation, and the z coordinates, so it's a linear distribution of displacement. It's a rigid rotation, and you don't have yet stress related to this displacement. Okay? Now I go to the first significant order, the leading order, what then gives you the Kirchhoff law plate model, okay, in the asymptotic framework. So this was demonstrated first by Schaller and Destunder, quite early, and followed by Kairi for periodic plates. And then what happens? You have the first significant contribution for stress. The first significant contribution is superposition of the curvature, the second derivative of the deflection. So it's the curvature times a localization field, which is actually just the in-plane bending stress. Okay? So for those who like beams, it's like Navier formula for having the bending stress inside the beam. Okay? So this is for the stress. And for the deflection, this is really important actually, you have a correction of out-of-plane Poisson's effect. Meaning you bend the plate or you stretch it if it's a membrane, it just gets thinner. This correction is at the leading order, and you need to take it into account. And this solves for engineers, you have this contradiction of plane strain or plane stress plate models. This is inside the asymptotic expansion. There is no contradiction. When you stretch the plate, it gets thinner. When you bend it, you have this effect also. And now you have this expansion for the fields, but you can also find microscopic equilibrium just by simple integration of the 3D equilibrium through the thickness. And you get these equations, the equilibrium equations, which are actually Reissner-Millin equilibrium equations. If you look carefully, here you have the divergence, you have the shear force. It's divergence, and it has to compensate the out-of-plane load, so it's the out-of-plane equilibrium. The second line is here, you have the bending moment in plane stress times z, integrated through the thickness, and you have its divergence, and it's equal to the shear forces. This is why you have a generalized continuum, because you have two resultants with the internal length scale between them. Okay? So this is for Kirchhoff law plate model. As you can see, there is no transverse shear effects in those distributions. So we need to go higher in orders. If you go higher in orders, what you get is you have a very interesting stress distribution related to the gradient of the curvature, which carries or encodes the transverse shear effects inside the plate. Okay? And in terms of displacement, you have a correction which is, let's say, related to transverse shear effects, but which mixes some different contribution mechanically speaking. I cannot go too much into details. If you follow strictly the asymptotic framework, here you need to solve a macroscopic problem, but this macroscopic problem is just zero. You have no solution. This classical in 3D medium, you have the central symmetric symmetry. Here it's just the monoclinic symmetry which has this effect. Okay? So you don't have solution. We need to go one order higher again. If you do that, you will end up with something which is solvable. I mean, something. And you have the localization related to higher order Poisson's effect. I'm sorry about that. It becomes ugly. And you have stress distribution, which is also related to higher order Poisson effects. And at this order, you need to take into account the actual distribution of the load. So it makes things much more complicated. Okay? This is for the expansion. Now, if you look carefully in the macroscopic problem you need to solve, what you find out is that you need to compute the sixth derivative of the displacement field. I don't talk about the boundary conditions, okay? So this is for the asymptotic framework. I mean, it's impractical. It gives loads of information, mechanically speaking, but it's impractical. Okay? So most people, what they are trying to do, and we're all trying to do that here, is can we have a direct problem to solve a plate model? Okay? So you'd switch to variational arguments, some truncating arguments, or whatever. You have all your favorite tools for doing that. I will just show the limitation of a very well-posed approach, which is what suggested by Smyshev and Cheredichenko in 2000. And it's well-posed, meaning that you have a well-posed problem in the end, because you have the sign paradox we talked about. If you're not careful, you will have the sign paradox, and with problem with that. So they suggest just perform a truncation of the displacement field, and compute the potential energy, and you have a plate model. Okay, let's do that. If I do that, I take the first term, there is no energy, it's rigid. Okay, second term, you have this rotation in addition. Then, if you do that, we will have a plane strain Kirchhoff law model. Actually, the model derived by Kirchhoff, with his assumption of no out-of-plane displacement. But we understand that this is not physically consistent. Everybody wants a plane stress plate model. Okay, so this doesn't work, and we don't have transverse shear effect anyway. So you can go one higher order. If you do that, you have this contribution, which is the out-of-plane Poisson's variation, which is included in the model, but not the transverse shear effects we are looking for. So if you want the transverse shear effect, you need to go, again, one order higher. If you do that, you're happy, you have all this displacement field, and if you compute the energy, you will have the second gradient of the curvature, meaning C4 regularity for the displacement field. Now the boundary conditions are just a bit better, but still impractical. So this is a limitation of a pure displacement approach, and we'll try to show you that if you have some other with static arguments, you can build a very efficient plate theory. So the bending gradient plate model. If you remember, I just truncated the displacement field. Now let's look at the stress displacement field, the stress field, the expansion of the stress field. Actually, what you need is just two terms. The first term, which is the in-plane or the bending stress. If you go one higher order, which I did, you have this contribution which is related to the gradient of the curvature. Okay? And this is really related to transverse shear effects. In this distribution, you have the Reissner parabolic stress distribution, actually. Okay? This is hidden in the formalism I've chosen, but it is inside. If I perform a change of variable, and this is not neutral, but I do that, I want to privilege the bending moment using the constitutive equation of the bending, so the Kirchhoff constitutive equation, and I choose to introduce its gradient, so the gradient of the bending moment, which is actually related to the gradient of the curvature. From the constitutive equation, I just introduced it there, which is this is the bending stiffness. Okay? So the relation between the gradient, the bending gradient and the curvature is pretty clear. If I do that, I could just perform a change of variable. I have this bending gradient stress field, which is related to the bending moment and the gradient of the bending moment. So using Hill-Mendel principle, averaging of energy, whatever you can call it, I just have a constitutive equation once I have a localization. Okay? So here, if I compute the the energy of this stuff integrating through the thickness, I get the bending compliance, -1, so the bending energy. And here something which looks nasty, but it is not. Something which is related to transverse shear effects. Okay? This tensor is just a 6-order tensor. So I like Samuel's notation about moustache, and I'm just a bit frowny today, but okay, but just 2 frowns for a 6-order tensor. And this tensor is positive from this approach, but is not positive definite. Okay? It follows some symmetries. I won't go into details about that. So I have a constitutive equation. What do I need for a plate model? I need equilibrium equation because it's a complementary energy, it's a stress energy. So I need equilibrium equations. Alright, what do I choose? Actually, I will choose Reissner-Millin equations, equilibrium equations, which are derived directly from integration to the thickness of the 3D equilibrium equation. So they make sense. But since I introduced the gradient of the bending moment, instead of choosing, instead of setting the shear force as the divergence of the bending moment, I will say that the gradient of the bending moment is the gradient of the bending moment. Sorry, but this is what it means. And this is just the extension of, here you have the divergence of the shear forces. Here is just the same equation. And the mechanical meaning of R is just that instead of mixing different components of the gradient of the bending moment inside the shear forces, I make this distinction between them. Okay? And this is really important for heterogeneous plates. Okay? Now, it's classical to dualize those equations, and it's very classical formalism. I will do in parallel the Reissner-Millin approach and the bending gradient approach. Okay? So for Reissner-Millin, you have the deflection. You multiply the out-of-plane equilibrium with the deflection, and this relation with the rotation. Here, I need a generalized rotation, which is a 3rd-order tensor. That's all. Okay? So it's just the dual quantity of R. And if I do that, so this is again the equilibrium, which is the only difference between Reissner and bending gradient theory. You can write the work of internal force and the work on the boundary. So I won't go too much into detail. We could discuss that later. The approaches are very similar, but you have a 3rd-order tensor inside the work of internal force, as well as the boundary, and you have additional boundary conditions, obviously. It turns out that when the plate is homogeneous, the electricity F, the transverse shear constitutive equation, which is a 6th-order tensor, it loses its elasticity, and it exactly turns the bending gradient plate model, which is into the Reissner-Millin plate model. Okay, because the plate is homogeneous. That's the first point. The second point is that if you look carefully in the work of the internal forces, I have only 1st-order derivative of the displacement fields. Okay, so this is really important in terms of numerical implementation and practical understanding of the plate model. So this is it for the bending gradient plate theory. Now I will try to build error estimates. Okay. So let's assume that I've solved the bending gradient plate model with the very efficient finite element models, which is not obvious, but anyway. I will use the 2-energy principle. So I didn't know that a few months ago, so I will try to recall this to you today. So the 2-energy principle is just the idea that if you have an approximation of the stress of the exact problem, so let's assume that sigma hat is a statically compatible field, but not the exact field, and you have a displacement field which is also kinematically compatible. If you compute the error between them in terms of constitutive equation, okay, this norm is defined there. If you compute the error in terms of constitutive equation, it turns out that it is strictly equal to the sum of 2 terms. It's just Pythagoras theorem. It's equal to the sum of the error with respect to the exact solution, plus in terms of stress, plus the error in terms of deformation with respect to the exact solution. So it's an estimate of we are trying to Okay, to have a range to estimate the distance between sigma and u, and it's exactly equal to the error with respect to the 3D solution. It just comes for the orthogonality relation, which is below, and which is quite well known. Okay, this is not new. This was used by Prager. It was defined by Prager and Singh, and used by Morgenstern and also Schwab, Bryce, and coworkers for plate theories, but homogeneous plates. Okay. So, I will use this principle. So I need to build admissible field, admissible approximation of the stress and the displacement fields. Okay. So let's assume that the plate problem is solved. So I know those macroscopic fields, and I can suggest the following field risk construction. So this is the displacement field I suggest. So it's very long, it's just scary, but no, it's not scary. It's just the asymptotic expansion. But I just replaced the curvature of the asymptotic expansion with the curvature of the bending gradient plate solution, as well as for the last term. Okay. So this is for the displacement field, and I can build also a stress which is compatible. Okay, so I need the first two terms I've used to define the bending gradient theory, and I need to add some pieces of the next order inside the stress, inside the definition of the stress. And if I do that, I manage to have a stress field which is compatibly 3D compatible. Okay, I will go into details into that, but you've satisfied the divergence equation, the equilibrium, and the boundary on the upper, the stress boundary on the upper and lower face of the plate. Okay, this is very peculiar to plate models, to this situation. If you do this with a 3D periodic medium, you won't have balanced, equilibrated stress field. Okay. So those fields are compatible, but this is very classical when you perform perturbation equations. They are compatible except on the lateral boundary of the plate, and these boundary conditions are weakly satisfied. Okay. So, assuming that I fulfill the boundary condition on the edge, okay, this is very common when we're in this situation. We have the following error. It turns out that if I compute the difference in terms of constitutive equation between the two approximation of the fields I've just suggested, I found out that it's proportional to the square of the small parameter times the leading order solution. Okay, the norm of the leading order solution. So provided that those fields are compatible, it's not always the case as I mentioned. You have the following estimates of the actual stress and strain fields. Okay, and if you do not fulfill the boundary condition exactly, it's far from the edge. Okay. Now I will very shortly give an illustration with Pagano's exact solution for the cylindrical bending of plates. Actually, it's a very nice configuration. You have an exact solution. In that case, you have laminated plates made of carbon fibers reinforced polymers layers, which have different orientations. It's an academic exercise in the composite community, and it's simply supported on the two infinitely long edges. And I made this drawing, but the exact boundary condition is this one. Okay. So the plate is invariant in the x2 direction and actually implicitly periodic in the x1 direction. So this peculiar choice of boundary conditions, you have no boundary layer, you satisfy the requirement for on the lateral boundary of the plate. So this is the boundary problem, the boundary value problem. I can solve this, and I show you the stress distribution through the thickness. So the three upper plots are the in-plane stress, so the bending stresses, so sigma 1, 1, 2, 2, 1, 2, and these are the transverse shear stresses. They look ugly. The blue is the exact solution, and the green is the approximated solution. They look ugly, but look, the slenderness is 1. So 1 is not slender for me. I don't know for you, but for me it's not slender. Now if I increase the slenderness, You can see that the fast convergence, look, we are just at 4. And for an engineer, at 10 I'm happy. Okay? So this is just an illustration of the stress state of the plate. And we can check this more precisely in terms of convergence diagrams. So on the left, I've plotted the stress error. For the blue curve is the bending gradient approximation I've just introduced before. And the green one is the Kirchhoff law approximation. And you see that you have different slopes, which confirms the error estimates I've just introduced before. Now, we must be careful. I've plotted also the error in terms of average deflection. And the blue curve is the Kirchhoff law deflection, and the green curve is the Kirchhoff law deflection, and the blue curve is the bending gradient deflection. Look, it does not converge faster. Okay? But it has 2 decades improvement in terms of error. So even if it's not faster, it's much better. So this is the end of my presentation. If there is something I want you to remember, is that I tried to give a formal justification of Reissner milling plate model by means of asymptotic approaches. Okay? So the ideas of Reissner are not so. I heard some people saying very bad things about him, but I don't see it that way. Okay, and if it's not homogeneous, then you need the bending gradient theory to have the same kind of approximation. Okay. The second point is that you have a low order of approximation of displacement, or low order regularity for the fields. Remember, I said I need the fourth derivative if I want to be correct, if I follow the strain gradient-like approaches. Okay? So we are intending to implement the finite element implementation, and going further in the boundary conditions. I mean, we have ideas not mature yet. And there is a nice application to cross-laminated timbers, because maybe you don't know that, but the contrast ratio between the stiffest modulus and the lowest one in the wood is about 200. So it's quite large. Thank you for your attention. Yes?
You don't do that?
No. It's inside, it's in the energy. Once I have the stress distribution, the transverse shear stress distribution, I compute the energy. And if it's homogeneous, you get the 5-6. But I don't want to think in terms of shear correction factors. I just think in terms of transverse shear stiffness. It's just a global information about the structures. Seeing that this as the first order shear deformation theory, when you assume that the transverse shear is constant, it is. I don't feel it very well. You see my point, or maybe I'm not clear.
I did a lot also on this shear plate, and we should discuss it or exchange it.
Just a comment, because we are in sense continuum, there are of course many different ways to obtain the Reissner plate model, and it turns out that you have a nice correspondence for linear model. There it is. You do a dimensional reduction by a purely mathematical under-free approach, and you get the Reissner model. The interesting observation is that Kosovar model has a triad of directions.
Yes.
And if you go down in the two dimensions, the two in-plane moduli, they disappear, and only the normal, which is not the normal of the final plate, remains. So it's a nice observation.
Thank you.
I don't know how to do it for the limiting.
Yeah, and to be frank, I don't know if I could introduce the drilling mode in this approach. I have no idea of the way of doing that.
Yeah, the drilling
does not exist. Yeah, it doesn't. The drilling mode, this one.
Yeah.
I don't know how I can include it in this approach. No idea.
No, the point is just you have a Kosovar model which has drilling, but when you reduce it to 2D, the drilling is absent.
Yes, you insist on it, yes.
Now you're the next superhero.